Welcome back to our Algebra 2 series. Today we are up to section 5.3 where we'll be looking at properties of logarithmic functions. In previous sections we've discussed that logarithmic and exponential functions are inverses of each other. So if y is equal to log base a of x, we can say that x is equal to a to the y power, and vice versa. So what happens when we take two things and multiply them together and try to take the logarithm of that product? Well, it turns out it's pretty simple. It splits into log base a of x plus log base a of y. Now you may be wondering, how do we get to addition when we started with multiplication? Remember, we're working with exponents here. Back in Algebra 1, section 3.1, we learned that when you multiply two things together that have exponents but the same base, you add the exponents. So a to the m times a to the n equals a to the m plus n. We started with multiplication and we ended with addition. This is why log base a of a product is equal to those two logs added to each other. So let's look at an example. Log base 2 of 4 times 16. Well, we just expand it out. That equals log base 2 of 4 plus log base 2 of 16. Keep in mind that a logarithmic expression is just the inverse of an exponential expression. So if we have log base 2 of 4, what does that really mean? We can say that 2 to some power equals 4. So in this case, that exponent mystery is 2. 2 squared is 4. So log base 2 of 4 is equal to 2. So we know that log base 2 of 4 is 2. What about log base 2 of 16? So 2 to that mystery exponent that equals 16 is 4. So at the end of the day, log base 2 of 4 times 16 is equal to 6. So what happens if we take a logarithm of a fraction or a division? Well, as you probably guessed, now we subtract. So log base a of x over y is equal to log base a of x minus log base a of y. So what about this example? Log base 3 of 7 over 11. We can simply rewrite that as log base 3 of 7 minus log base 3 of 11. In this case, it can't be simplified any further. So what happens if we take the logarithm of an exponent, log base a of x to some power, in this case p? Turns out this is pretty easy. When you take the logarithm of something with an exponent, you can simply pull the exponent out and put it in front of the logarithmic expression. So log base b of 9 to the 5th power is equal to 5 times log base b of 9. What about combining them all? What would you do with that? Well, for that, let's jump over the whiteboard and do some examples. Okay, let's start up here with log base, we'll say x of b times a. And just to clarify, we're going to put brackets around this so we know that we're taking the logarithm of this entity here. So we have a multiplication, so it would be log base x, let's finish that g, of b, the first part of the product, plus log base x of a. We're taking the product and it splits into addition in the logarithmic world. Let's do an example with some actual numbers here. Log base 3 of 27 times 81. So let's do the first step and just rewrite it. We have a product, we're multiplying two things, and we'll split it out into two things being added together. Log base 3 of 27 plus, we've turned it into an addition, log base 3 of 81. There we go. So now when we look at these, we got 3 as our base. We're taking log of 27 and 81. This might set off some alarm bells in your head. We can simplify this further. So basically we're saying 3 is our base to some mystery power equals 27. So I'm going to invert this. We're going to use our inverting powers to take this first expression and say 3 to the mystery power equals 27. These two expressions are invertible like that, taking a exponential expression and inverting it to a logarithmic, or the other way around. And we can do the same thing over here with our inverting powers. 3 to some mystery power equals 81. So 3 to something equals 27. 3 times 3 is 9 times 3. Oh, it's 3. So here, the first question mark is a 3, because 3 cubed is 27. And here, this one is 4. 3 to the 4th power equals 81. So this expression really just equals 3. This expression really just equals 4. So the answer is 7. There's nothing stopping us from going the other way around. We can take log base a of, we'll say 6, plus log base a of 8. So we're adding two logarithms with the same base. It's important you have the same base. And it really just turns into a simplified expression, log base a of 6 times 8. And we could simplify this even further and say log base a of 48. Let's clean this off and do some more examples. I want to do another one of these examples where we have a logarithmic expression, log base, we'll say b, of a fraction. We'll say 3 over 4. So we're taking the logarithm of division or a fraction. So now we would subtract those two bits and pieces. So this equals to log base b of 3 minus log base b of 4. And we can do the same thing if we had, let's say, log base 10 of 47 minus log base 10 of 17. We could rewrite this as log base 10 of 47 over 17. This is a weird fraction. We would probably just leave it like this. Let's clean this off and do a bonus complicated problem. Okay, this is going to be in doozy category, but I know we can do it. Log base a of the fourth root of x, y over z cubed. So what we want to do is change this expression in terms of x, y, and z. So what we got going on here? We have some multiplication, x times y. We have division going on here. We have exponents. We've got a fourth root. What's that all about? So let's do it one thing at a time. What we're going to do is just rewrite this as log base a of x times y over z cubed. And to get rid of this radical sign, we'll just write it as a fraction to the 1/4 power. Remember, when you have a fractional exponent, the bottom becomes a root like this. So we have something really easy staring at us. We're taking the logarithm of some horrible thing, but that horrible thing has an exponent. So we're allowed to take any exponent of a logarithmic expression and just throw it out to the front. So let's rewrite it over here, give ourselves plenty of room, and that 1/4 just pops out in front. 1/4 times the log base a of x, y over z cubed. So it's already a little bit simpler. And we'll put an equal sign because it's equal. So let's tackle this division. We have a thing being divided by another thing. And we're taking the logarithm of that fraction. So, of course, we're equal, and we know we have a 1/4 out in front of everybody. This will be 1/4 times now this entire entity. Log base a of x, y minus the log base a of z cubed. We took this division, this fraction, and made it a subtraction of two logarithmic expressions. And when we did that, you can see now we're taking the logarithm of something to an exponent. So this 3 can come out in front of this logarithm. I'm going to write it all out, and it's going to take up a little bit of space here, but that's fine. It's 1/4 times, again, this whole mess. We're not doing anything with this xy yet. We'll just rewrite it as log base a of xy minus this we're going to change. We're going to bring the 3 out front. 3 log base a of z. The 3 can come out in front of this expression. That's what we did. Log base a of z. We still have a product here. We're taking the logarithm of a product. So we'll give ourselves nice of plenty of room here. 1/4 times the logarithm base a of x plus the logarithm base a of y. I took this expression and turned it into these two expressions. A multiplication of the logarithm becomes addition. And we just write the rest of this 3 log base a of z. This a should probably be a little bit lower because it looks so confusing, but you get the idea. So now we've taken this crazy expression and broken it out into a log of an x, log of a y, and a log of a z. That's it for today. We'll see you next time.